In this video, we're going to be discussing the work done by electric fields and then transition into a discussion of the potential energy stored by particles in an electric field. To begin with, we will talk about work, which is defined as the force applied to some object dotted with the displacement of that object. Remember that the dot product is a way of multiplying two vectors together that gives a scalar value. The work is a scalar value. And remember that the work is equal to the change in energy of a system. So the work done on a system is equal to the change in energy for that system. For example, if I have a ball and I throw that ball, I apply a force on the ball over some distance, and I change the ball's energy by giving it kinetic energy, for example, right? I do work on the ball as I throw it, and it has an increased energy once I'm done doing that work on it. Okay, in the same sense, if I do positive work, I increased the energy of the system. I have a positive delta E. There's more energy after I did the work than before. If I do negative work on a system, then I took some energy out, then the system has less energy than it started with. So an example of negative energy or negative work is the brakes on your car, right? When you apply the brakes on your car, you are taking energy, kinetic energy, out of the system by using the brakes. So your change in energy is negative. You have done negative work by pushing on the brakes in your car. Okay, so we're gonna see positive and negative work in two examples here. Before we do that, I just wanna note that the more formal definition of work here is the integral of the force dotted with the displacement, or dl here. And this is useful if we have a non-constant force. So if the force changes over the displacement, maybe I push hard in the beginning and then I don't push as hard on some object. Later on, my force is changing. I need to take that into account by doing an integral. We're going to start out by simply using this simpler definition, which works for constant forces. All right, so with that kind of intro, let's think about a specific example of finding the work done by the electric field. So I have a positively charged particle that has some displacement to the right in an electric field pointing to the right. I know that the force on that charged particle points to the right and has a value that is equal to charge multiplied by the electric field. This is just our relationship between charge and charge, electric field, and force. So I can write down the electric field in terms of as 5 newtons per coulomb x hat. This is just a value for the electric field that I made up for this example. I have a 3 coulomb charge and it moves in the positive x hat direction. Taking this dot product, I have 3 coulombs times 5 newtons per coulomb in the x hat direction dotted with my 1 meter in the x hat direction gives me 15 joules of total work. I added energy into this system. How do I know? Well, because as I apply a force to the right here, that is going to cause this particle to speed up. It's going to gain kinetic energy as that happens. My electric field did positive work. That positive work translated into a positive change in the kinetic energy of the particle. All right, so the next thing we can look at is what if I did the exact same displacement in the exact same electric field, but now I have a negative particle. Well, now my force points to the left. Doing exactly the same work equation, I now have a minus sign out front from my negative charge. My electric field vector hasn't changed, my displacement vector hasn't changed, but now due to the negative charge, I have negative 15 joules of work. This makes sense in terms of doing negative work because now my particle is moving to the right while it's experiencing a force to the left, which is going to slow down the particle. So if my particle initially has some velocity to the right, it will have less and less velocity as the electric field acts on it, as we feel this force against the direction of velocity, right? This is leading to negative work done by the electric field and a loss of energy, in this case specifically kinetic energy, for the particle. Now let's move on to talking about electric potential energy. So, the electric force is what is called a conservative force. And the definition that we are going to use for a conservative force is that any work done against a conservative force is stored as potential energy. So the classic examples that you've seen in Physics 1 would be gravity or springs. So for example, if I have a marker, if I do work against the electric field by lifting the marker, right? I am doing work on the marker against the direction of the electric force. As I lift the marker, I am storing potential energy, and I can get that potential energy back out by allowing the gravitational force to do work on the marker, right? So in the Physics 1 case, we used the gravitational potential energy as opposed to thinking about work done by gravity, right? We would just consider mgh, that is the potential energy stored in the gravitational field, and we would include it in our overall energy calculation. And we're going to do exactly the same thing with electric fields, because electric fields and the electric force is a conservative force in exactly the same way that gravity is. Any energy that I put into doing work against the electric field is stored as potential energy that I can then retrieve by just letting the particle go, right? So for example, say I have a charged particle sitting here in an electric field. If I simply release that charged particle, it's going to follow the direction of the force on it and accelerate this way, right? That particle has some stored potential energy. How do I know? Because as soon as I release it, we get that potential energy out in terms of kinetic energy. Just like when I release my marker, I get the energy out of the marker. That potential energy turns into kinetic energy naturally. Okay, so the electric force is a conservative force. I can store potential energy in it. And I get 100% of the work out. So any work that I put in against the electric force, say to get the positive Q here, say I had to lift it up to this location, doing some amount of work, I could release it and get that work back as kinetic energy. That's what makes the electric force conservative. Okay. So what we want to do is we want to use our relationship between the work done by a conservative force and potential energy in order to come up with an equation for the potential energy stored by some particle. All right, so the equation that we're going to use is that the change in potential energy for any conservative force is equal to the negative of the work done by that conservative force. So in the case of the electric field, the change in the potential energy, the electric potential energy of a particle, is equal to the negative of the work done by that force. In this case, the electric force. To begin with, let's take a look at the familiar example of gravity. So imagine that I have a massive particle, a ball, say, in a gravitational field. It is experiencing a force due to gravity downwards, and imagine that I lift that ball upwards. I know that I'm going to be increasing the gravitational potential energy of that ball, and I know this because the gravitational field, or the gravitational force, is doing negative work as the ball is being lifted. We can see that if we simply calculate it. The work done by gravity here, I have negative mg y hat as the force on my particle. I have some delta y hat as the displacement of my particle, which leads to negative mg delta y, right? This is the amount of work that gravity has done on the ball as it is lifted. It's doing negative work, which means it's storing positive potential energy. Likewise, if I release the ball and allow it to fall, gravity is going to be doing positive work because it is applying a force in the direction of motion. That gives us positive work, but I lose potential energy due to this minus sign. All right, so now let's apply the exact same logic to our electric field case. So imagine that I have an electric field pointing downward. Well, the force on my positively charged particle here is also downward. And just like in the gravitational field case, if I release the particle, it's going to experience a force downward due to the electric field. The electric field is going to do positive work on the particle, which is going to lead to a loss of potential energy of the particle. Likewise, if I lift the particle, well, then the electric field is doing negative work, right? The force of the electric field is in the opposite direction of the displacement of the particle. The electric field is doing negative work, which means I am storing positive potential energy in the field. You can also think, well, imagine that I want to figure out how fast the ball is going to be going when it reaches this point. If I release it from this point, it'll have this distance to gain speed through the electric field. But if I lift it higher, well then, now when I drop it, it's going to have a much longer distance to gain speed. It's going to have more energy. Where did that energy come from? It came from the potential energy of the ball stored in the electric field. Right? Now let's look at the example of a negative charge. Well, we have an electric field pointing down, same idea, but now our negative charge is feeling a force upwards, which means if I simply release this charge, it will naturally move against the electric field in the upwards direction. That means that if the particle moves upwards, it is now having positive work done on it by the electric field, which means it is losing electric potential energy. If I want to store more energy in this particle, I need to pull the particle against the electric force downward. So now moving downward with this negatively charged particle will increase its electric potential energy because the electric field will be doing negative work. I will be storing more energy. Now let's look at an example of using the change in potential energy for a particle in a uniform electric field pointing to the right. So we have a charged particle here with a charge of +5 coulombs. We have an electric field that is uniform pointing to the right of a magnitude 10 newtons per coulomb. And what we want to do is we want to calculate how much does the potential energy of our charge change as it moves to the left or to the right within this electric field. So we have 3 different locations that we are going to move our charge to. So from its initial position, we'll move it to A. Then we'll say from its initial position, we'll move it to B. And also from its initial position to C. And we want to see how does the change in the potential energy vary as we move to these different locations. Okay, so we are going to use our change in potential energy equation here, which is the negative of the work done. Right? So the change of the potential energy, the electric potential energy specifically, is equal to the negative of the work done by the electric field. Using our familiar equation here and plugging in our values for the electric field and the displacement is -1 meter x hat because I move 1 meter to the left here in the negative x hat direction. The 2 minus signs cancel out and I get a total of 50 joules of positive potential energy. So the potential energy of the particle increases as it moves to the left here. This makes sense based on our intuition because the force on this particle due to the electric field is to the right. When I move against a conservative force, I increase my potential energy. All right, let's see what happens when we move to point B. So to get to point B, we're going to travel along this line here. This is our displacement vector. And what we can see is that we're going to move in the x direction and we're going to move in the y direction to get to point B. Looking at the math here, we have the same q times the electric field, and then we dot it with the displacement, where here we have a negative 1x hat minus 1.5 y hat. Now, remembering how the dot product works, we multiply the x component by the x component and the y component by the y component, and then we sum the result. But we don't have a y component to the electric field, so this y component of my displacement gets multiplied by 0 and does not add to our change in potential energy. So our change in potential energy to get to point B is exactly the same as the change in potential energy to get to point A. What we can learn from this is that the only thing that matters is when we move with or against electric field lines. Moving perpendicular to them does not change our potential energy. The gravitational analogy to this is I can increase the gravitational potential energy of my pen by lifting it up or dropping it. I could decrease it by dropping it. But if I move the pen side to side, I am not changing the potential energy due to gravity of my pen. That is because I'm moving it perpendicular to the gravitational force. The gravitational force points down. If I move it side to side, I am not working with or against the gravitational force, so I am not changing the potential energy. So, going from this location, my starting location, to A, I gain the same amount of potential energy as moving from my initial location to B. Now let's look at point C. For point C, we're going to be moving with the force, the electric force here, because we have a positive charge moving in the direction of the electric field. Using our equation, we now have a displacement of plus 1 meter in the x hat direction, minus 1.5 meters in the y hat direction. Again, when we take our dot product, the y component gets multiplied by 0 and does not influence our change in potential energy. And we end up with a change in potential energy of minus 50 joules. This makes sense again from our previous discussion, because when we move with the direction of the electric force, we lose potential energy. Now let's use this same example to talk about something called path independence. Path independence means that the change in potential energy depends only on the initial and final locations of the particle, not on the path taken to get there. We can think about this using a gravitational analogy by thinking about a pen that starts at this height and ends 1 meter above its initial location. It doesn't matter if I lift the pen directly up, if I move it to the side and then lift it up, if I lift it up and then I lift it up more and then I bring it back down. Any of these options, it only matters for the change in the potential energy total. Where did I start and where did I end? Specifically, what height did I start at and what height did I end at? And so in this case, the change in potential energy is going to depend only on how far left or right of my starting position do I end up. So what we're going to do is we're going to take two different paths to get from my starting point to point B and see that they in fact both lead to the same result for our change in potential energy. And though these are only two paths, it actually works for any path, in fact. So let's see how these two paths work. First, we'll follow this red path where we go from my point charge, or from my initial location to point A, from point A to point B. So we can say that the change in potential energy from my starting point to point A is 50 joules, as we found before. The change in potential energy as I move from point A to point B, so in the second leg of my journey here, is going to be negative charge multiplied by field dotted with my displacement. My displacement is only in the y direction. My electric field is only in the x direction, so there is no work done and no change in potential energy between these 2 points. So my total change in potential energy goes like the change in potential energy to get to point A, plus the change in potential energy to get from A to B, and I end up with 50 joules, just like I found before. Now let's try going from my starting location to point C, and then from point C to point B. Okay, well, the first thing I do is I find the change in potential energy as I go from my starting location to point C. That we find to be negative 50 joules, just like we did before. And now we go from point C to point B. Charge multiplied by electric field dotted with my displacement. Now my displacement is 2 meters in the negative x-hat direction because I have to go 1 meter to get back to where I started, another meter to get to point B, and that leads to 100 joules of potential energy that I gained. Adding these 2 changes in potential energy together gives me a total of 50 joules of potential energy change for this system, which is exactly what I found when I went straight to point B or from my starting point to A to B. All of these will give the same result, and I would even get the same result if I did some weird loop-de-loop path to get there. It only matters where I start and where I end. Now let's do a specific example of using this electric potential energy to solve a problem. And this problem is going to look a lot like a projectile motion problem that you might have done in Physics 1. So the setup is that we have an electron here, which has some initial velocity up and to the right, and it's going to follow a path similar to this blue dotted line, where it's going to reach some maximum height and then start moving in the opposite direction. So first, let's just analyze how I know that that's the path that it's going to take. Well, if you look at the electric field points straight up. The charge is negative, which means that it is going to experience a force straight down. Because the electric field is uniform, that force straight down is going to be constant on the particle, just like the force of gravity would be. So this is going to look a lot like a projectile motion problem that we're going to solve with energy that you might have solved in Physics 1. Okay, so the things that we need to know are the charge of the electron, negative 1.6 times 10 to the negative 19th. We need to know the velocity and the angle of the electron's initial velocity. And we need to know the magnitude and direction of the electric field here. Now, what we're looking for is the height, the maximum height above its starting location that the electron reaches, and the velocity of the electron when it reaches that height. So to begin with, what we're going to do is we are going to choose a 0 point for our potential energy. In this case, it's our electric potential energy that we're going to choose a 0 point for. Just like you did in Physics 1 with gravity, where you always have to pick a 0 of your gravitational potential energy, the same thing is going to happen here with your electric potential energy, where we need to pick a 0 point. We're just going to pick the point where we first start observing the electron to be the 0 point. Now, we're actually going to completely ignore gravity when solving this problem, and after we solve it, we'll go back and we'll see why that was a valid assumption to make. Now, because we're going to solve this problem using energy, the first thing that we're going to do is we're going to write down the initial energy of the particle. Well, it's at our potential energy equals 0 line, so it does not have any electric potential energy. So the initial energy is only kinetic energy. 1/2 mv squared. In the final state, it has some amount of potential energy because it has moved against the electric force, which again points down here because it's a negative charge. So it has gained some amount of potential energy, and it still has some amount of velocity. That velocity is only going to be in the x direction, however. Remember, when a particle is at its maximum height, it is moving only in the direction, the x direction here. Now what we can do is we can look at the initial and final energies and equate them to one another. We know that there's no non-conservative work done. There are no outside forces. There's only the electric force here. and the electric force is giving us potential energy. So what we can do is we can set our initial kinetic energy equal to our final kinetic energy plus potential energy. And now what we're going to do is we're going to use our knowledge about the final velocity. We know that the final velocity is only in the x direction, and that there were no forces in the x direction which would have sped up or slowed down the particle in the x direction. So that means that our final velocity here is just v naught x. That is, our initial velocity in the x direction is the entirety of our final velocity. Likewise, we can write our initial velocity explicitly in terms of x and y components. And we can write v naught squared as v naught x squared plus v naught y squared. And we can actually separate this into two independent terms, one depending on v naught x squared and one depending on v naught y squared. And we now have a term that looks like 1/2 v naught x squared on the left and a term that looks like 1/2 v naught x squared on the right, which will cancel each other out. So after that cancellation, we find that our 1/2 m v naught y squared is equal to the potential energy gain of our system. That is, we traded our y kinetic energy for electric potential energy. We can use our equation, which is the change in potential energy equals the negative of the work done by the electric field here, where we are taking the dot product of the force with the displacement in y. Again, we don't care about displacements in x, only displacements along the direction of the electric field actually contribute to changes in potential energy. So we don't need to care about how far it moved in the x direction here. We only care about how high it is above its initial point when we're calculating this potential energy. All right, so our displacement in y is y final minus y initial, which is just h. Dotting this with our electric field, which is also in the y direction, we arrive at this equation here for our potential energy. Now, you're probably thinking, why is my change in potential energy negative? I thought that I was moving against the electric force, and therefore I should be gaining potential energy. Well, the Q here is our electron charge, which is also negative. So we have a negative out front and a negative charge, which makes this whole term positive. So we have, in fact, gained potential energy. And we've traded our kinetic energy in y for positive potential energy. Solving this out, we have h equals 1/2 mv naught y squared over q times the magnitude of the electric field. And that gives us 0.57 meters as the height that the electron has gained. To finish up this example, first let's find the final velocity. Well, we've already argued that the y velocity must be 0 when it reaches its maximum height, and therefore the final velocity must simply be its x velocity, so its initial x velocity, which is 400 meters per second multiplied by the cosine of 30. Okay, and now finally I'd just like to argue that it was a pretty reasonable assumption to ignore gravity and the gravitational potential energy when doing this problem. So first, if we just look at the forces on this electron, the force due to the electric field was 3.2 times 10 to the negative 24th newtons, which is obviously a very small force. However, the gravitational force is 6 orders of magnitude smaller at 9 times 10 to the negative 30 newtons. Likewise, when we calculate the change in the gravitational potential energy and the change in the electric potential energy, as it rises to its max height, we find that the change in the gravitational potential energy is 6 orders of magnitude smaller, 10 to the negative 32 versus 10 to the negative 26 for the electric potential energy. So if we had done this problem where we included the gravitational potential energy, it only would have changed our answer if we were interested in an answer that was more than 6 decimal places in accuracy. Otherwise, this gravitational potential energy would not actually influence our final solution. And because we weren't interested in that level of accuracy, it was completely reasonable to leave out the gravitational potential energy in our calculation.